is a constant number. And depending on the configuration that's given to you, you have two configurations. One is when there's a constant wall heat flux, then your Nusselt number is governed by that. And the other configuration is when you have a constant surface temperature, and your Nusselt number is given by this expression. So anything that's in the entrance region, that's when your H value is changing. So if it's changing as we goes into your X, as we go across X, if it's changing, then your Nusselt number would vary actually. Okay. Now this other one, sort of like answer a little bit of what you have in this question over here. So this Y is also partially answered over this first sentence. It says that within the entrance region, the boundary layer, and boundary layer refers to your thermal and hydrodynamic. Now your hydrodynamic, sometimes there's another word for that, there's velocity. So your thermal and your velocity boundary layers are growing axially, and therefore the heat transfer coefficient varies with X. So that was very similar to what we responded over here. So it asks, why is it that the heat transfer rate decreases as X increases? So X, again, is relatively from the entrance of your pipe. So why is it that the heat transfer rate decreases as X increases? So as X increases means that it's going along the pipe that way. So obviously your heat transfer rate will decrease because of the following. Because some heat would have already transferred. Upstream. So what does that mean is that in your entrance region over here, as the flow moves along, some of the heat would have already gotten transferred. So might it be transferring in or transferring out? But as it flows along the pipe, some of the heat would get transferred already. So further down in your pipe system, there will be decreasing heat transfer rate as X increases. So that's the reason why. Now I want to spend some time introducing what this figure is about. Again, you have this split up into the following region. Your entrance region over here, and your fully developed region over there. So really this point is when you have your fully developed conditions, and they are reached over here. So there are two graphs over here. One would be at your Nusselt number when it's equal to 4.36. And the other one is when you have your Nusselt number at 3.66. So if you look back what you had before, this Nusselt number, that's 4.36, was for the case when you have a constant heat flux. And this case, when it's 3.66, is when you have the surface temperature that's constant. So you could see that because their respective H value will be constant. So in a fully developed region, along the Nusselt number axis, you would see that the case when you have a constant surface temperature is at a constant value over here. And for the case when you have a constant heat flux, you have a constant value over there. So in the case of your entrance region, you would see that for your constant heat flux region, there will be two lines. One line is given by this, and the other one given by your dotted line. The same goes for the case when you have constant surface temperature. You have a solid line over there, and then a dotted line is over here. So what are all these solid and dotted lines? So in this legend, it says that the dotted line refers to thermal entry length. And I'm going to write down a little bit to explain what is the meaning of the thermal entry length. What it means is your thermal conditions develop in the presence of fully developed velocity profile. And what that means is there is an unheated starting length. For the combined entry length, what it means is the temperature and velocity profile develop simultaneously. Now, these are words, but what does it mean? It means that if you have your pipe system, and if this is a region of your fully developed flow, what it means is that your heating actually starts from over here. And over here, this region, there's actually no heating. So your entrance part don't have heating, but the heating only comes in after when it's fully developed. So you would see that a lot of setups that we have for a pipe system, your entrance region where the fluid starts to flow in, that region is actually a very, very tiny region. And your fully developed region is when you use most of your heat transfer. That's for the rest of the pipe that's going through the entire network. So it's that fully developed region that you are more concerned with. And that's when if there's heat transfer, might it be going in or going out of the pipe, that is when you have your heat that's transferred. So that refers to the dotted line over there. And for that solid line, what it means is that it's not only this fully developed region that would have heat that's transferring, but also your entrance part. That's why it's combined. So that's the meaning of that. So if you have your combined entry length, you could see that relatively your Nusselt number would be of a higher value compared to the case when you only have heating or heat transfer after your fully developed region. So that's what this figure is trying to show us. And also, this figure is plotted with Nusselt number versus this symbol over here, GZ. Now, this is not subscript Z. It's actually capital G and a small letter Z. And this is called your, how do you pronounce this? Okay, you can develop your own way to pronounce it, but I pronounce it as Griggs number. Right? So Griggs number is actually given by the following equation, x over d, RED PR over x over d. Now, one other thing that I want to highlight is also you're going to see D as diameter written as capital letter D. In various textbooks that you see, sometimes it will exist as small letter d. Particularly in your exam data booklet, it's written as small letter d for diameter. But in this case, your notes material is writing it as capital letter D. They mean the same thing. diameter of the pipe. Okay. So what is Greig's number? Now Greig's number is telling us about where is the place where we consider is an entrance region and a fully developed region. So at certain Greig's number, we'll be able to figure out, like, are we talking about your entrance region, or are we talking about your fully developed flow region? So that's what Greig's number job is about. So the heat transfer coefficient in the entrance region is usually expressed in terms of your Greig's number, and that's given by this equation over here. If you look at your exam data booklet, Greig's number is not included inside. Right over here, you can see this one is actually Grashof number, it's not Greig's number. Greig's number is GZ, is GR. And later on, we'll be talking about Grashof number. So again, like I say, there are some things that are not included in your exam data booklet, so it's something that we'll highlight in the class. Now it can be shown that the Nusselt number, you can see that it's varying as it goes, as it enters into your entrance region. And this expression for this curve over here can be given by this equation. And this equation, again, is also not included in your exam data booklet, and I'll be highlighting that in class. Now what is this equation about? It's actually for the thermal entry length, and rightfully there should be a D over here to say that this Nusselt number refers to the pipe system, and there should be an overbar over there to signify that it's an average Nusselt number, where you have seen before for a Nusselt number is equal to H D divided by K. So later on there will be an example to show you how do we go about using all these various expressions to help us to solve. So in this one, this set of equations here is for the thermal entrance length. Right, again, this is used for in this entrance region. So please note that these are the configurations that I often point out what this equation is used for. This equation is used for your entrance region. So later on, for the fully developed region, we'll be using another set of equations. So there are really a lot of sets of equations for different configurations. Thermal entrance length or combined entrance length with Prandtl number that's approximately greater than 5. So these are again always. Later on we'll have an example so that it allows you to see clearly how do we go about making use of that. So I want to highlight again this set of equations, that's for the entrance region. Now we're going to go into the region that's called your turbulent flow. Now turbulent flow is not fully developed flow. Right? Please take note of this. It's not. Fully developed flow is the part that's right after your entrance region, and then it goes into fully developed flow. As you move along further down the pipe system, that's when you will experience turbulent flow. How that turbulent flow comes about? Your fully developed flow, due to the viscosity, somewhere along the line there might be bends or surface roughness. That's when your fully developed flow will start to churn up, and then it will develop into turbulent flow. So most of your pipe system, unless you have very smooth pipes, most of the pipe system will experience turbulent flow after some point of time. There will be those turns moving around, and soon after you get turbulent flow. So let's look at your turbulent flow in circular tubes. Again, this turbulent flow in circular tubes, and not any other configurations. So please take note of this configuration. So your turbulent flow is a great feature for mixing purpose. So why would turbulent flow be a region of flow of interest to us? That's because in the turbulent flow, you get quite a fair bit of heat transfer out or in. Why is that so? You could imagine if it's laminar flow, you still get heat transfer in or out. But if it's turbulent flow, there's a lot of mixing that's going on in there. And hence, whatever heated surface or colder surface, if you have turbulent flow that's going around the surface, it actually encourages more heat transfer. So that's why turbulent flow is a study that concerns us, because if I were to ask you, how can I increase the amount of heat transfer, then the turbulent flow region would be of interest. So that's what I was saying. It increases the rate of heat transfer in the turbulent region. And your turbulent flows are much more capable of convective heat. So the kind of heat that's transferring from the solid pipe to your fluid that's flowing inside the pipe, that kind of heat transfer is convective heat transfer. So the unfortunate thing is that turbulent flow usually is very complicated and requires computation effort. Yeah. So the kind of equations that we have over here, the Nusselt number, that's for a fully developed, not laminar, but turbulent flow. Okay, so this is the other configuration. You had seen just now fully developed laminar flow, but this one is fully developed turbulent flow. So they have different set of equations over there. So if we want accurate readings at whichever part in your pipe, if we want the accurate reading of the heat, of the temperature value in whichever part of your pipe for a turbulent flow, we need to go through that computational method to figure it out, do a simulation for that. But that part is of the advanced level, and in your module we wouldn't be covering that. Instead, we'll be looking at a approximated equation to govern that fully developed turbulent flow, and this equation requires Reynolds number, Prandtl number, your viscosity, this US over here, or mu S over there, refers to your viscosity at the surface of the pipe. So later on we have an example to show you what does that mean. This S here refers to the surface of the pipe. In order to be able to use this Nusselt number, you see that it's only true if your Prandtl number resides within this range, and your Reynolds number rightfully is more than 10,000. So that's consistent with what we already know for a pipe. So if I just slide over here to your data booklet, you would see that for a turbulent flow, this is the Nusselt number expression. For a turbulent flow, usually it's more than 10,000 for your Reynolds number in order to signify that it's in turbulent region. So your Reynolds number more than 10K, and then your L divided by D, that L refers to the length of your pipe that you are interested in, and the D over there refers to the diameter of the pipe. So L over D, it is greater than 10, meaning that it's longer than its diameter. That pipe that you're concerned with is longer than your diameter. How much longer? 10 times longer than your diameter. In this case, then we can use this set of equation. So I've been talking about Nusselt number equation, but what is that and how to make use of that. Later on, there'll be an example to show you that. But for now, there are various different sets of Nusselt number equations for different configurations. So I just want to highlight that for now. So most of the properties, and properties over here refers to things like your density, your dynamic viscosity, things like your thermal conductivity, things like, say, your Prandtl number. So all these properties, they are found out using what we call your Tm average, that is the average temperature of the fluid inside the tube. So what that means is that if you have a tube, there will be a part that we call your temperature at your inlet, and a part over there that we call the temperature at the outlet. So since your turbulent flow is going on in there, then your turbulent flow would have various density, kinematic viscosity, thermal conductivity, Prandtl number at different points along your turbulent flow tube. Then in that case, which are your properties that you'll be using? You'll be looking at your average temperature, that is T M I plus T M O, your inlet and outlet, and take the average of that. So it's hard to say this without giving you an example, because you would see that at different temperature, you would have different density. A very easy way to imagine that is that for example, water. You would know that for water, at different temperature, it has a different density. So as your thermal conductivity, so as your kinematic viscosity. For water, at different temperature, you would have all these various properties. So since your fluid is going through the pipe and heat is transferring along the way, then what is my density that I consider? So the way to consider is to take the average temperature between the inlet and the outlet, and then we say that, okay, this is what we want to go for. That is the property. Okay. So now the temperature difference is not large. When the temperature difference they are not large, the following call relationship may be used. And this refers to this temperature difference over here. If your inlet and your outlet temperature difference, if they are not large, then you'll be using the following Nusselt number expression. So this following Nusselt number expression is actually very close to what you could see in your exam data booklet over here. Right. So you have that coefficient over here. You have that Reynolds number. Now 4/5 is actually 0.8. This power 4/5 is actually 0.8. Your Prandtl number, if it's for heating purpose, then your Prandtl power is going to be 0.4. If it's for cooling purpose, then your Prandtl number power is going to be 0.3. So you can see so many different configurations that you need to take care of. Not only turbulent flow, you gotta be concerned about if the temperature difference is huge, and if it's huge, is it cooling or is it heating up? So many different configurations. So what I want to do now is just highlight these different configurations, and later on we'll have an example to see how we can use that. You will see that there's another term over here. When you have your kinematic viscosity divided by the wall, this W here stands for wall, but in your set of notes, is said as surface. So the surface of the pipe, the wall of the pipe, they mean the same thing. So this part here is missing. That's because there's an assumption in this turbulent flow over here that your kinematic viscosity at any point in your pipe is the same as your kinematic viscosity at the wall of your pipe. All right. Now this is only possible if, let's say, the temperature difference between the inlet and outlet are not too big a difference. If they are very different, then we'll have this term kicking in. So these are some of the insights. It's hard to be memorizing all these various different configurations. So what you need not to worry, because all these various sets of conditions will be provided if needed. Okay? So again, you would see that in your data booklet, the only condition given is Reynolds number. As long as it's greater than 10,000, we say that it's turbulent flow. But over here in your lecture notes, it says some additional conditions. One is your Prandtl number got to reside between 0.7 to 160. You will see that your Reynolds number stays over there. And there's another condition about the length of the tube of the pipe that will be 10 times more than the diameter. So these are additional conditions. It's not reflected over here. So different textbook, they emphasize on different things again. If you look up Holman textbook, the lecturer in Glasgow often use another textbook that's by Incorpora. You would see that in my introduction slides, these are authors' name for another textbook. You see that in my introduction slides to you, on the first lesson that I have, I would have listed down a few textbooks. So one of them is Incorpora. You can refer to that textbook as well. So since it's so dynamic, then how do we go about having a good correlationship estimation for the convection heat transfer coefficient H? Usually, we will find that it would include error up to 25%. Now, this again, I often tell students that fluid dynamics, heat transfer, is an art. You know, it's an art. Why is that? It is an art. That's because the engineers, we often want to have one answer only. But because in fluid dynamics, especially in this case where you have heat is transferring out because there's a flow, the tendency is that your answer is good up to about plus minus 25%. That's a huge margin. It's hard to accept for an engineer because we are so used to having the answer must be 0.001 accurate. Yeah. But for this kind of very dynamic environment, you often get different textbooks saying slightly different things. That's because they can accommodate that amount of inaccuracy in their results because it's very dynamic. Your H value that you will be seeing in your lab, that's what your lab work is about, trying to find out what is the H value. You find that from student to student, the H value is going to slightly be a little bit different from each other. That's because there is that error. Your system depends on the kind of water supply by the building, and sometimes the pressure will drop. And this pressure drop is because someone else over the toilet there did that flush, and suddenly you have a pressure drop. So this kind of thing could happen. It affects your readings. So we try to accommodate that. We know that for that kind of dynamic fluid flow, we have about plus minus 25% of error. And that's a large error to accommodate. So in order to reduce that to less than 10% error, more complicated correlationships should be used. And in this case, it says that you could read up the textbook, for example. So I'm including one section that you could look at. If you have the Holman textbook, you could look at section 6-2, some of your empirical relationships for a pipe system. are seriously a lot more other complicated correlationships, the Nusselt number correlationships. So what I've shown over here in the slides, there are some correlationships over here, some formulas behind root Nusselt number with specific configurations. It's not exhaustive. It's not covering everything. Just because there are more complicated ones, just introducing the more simple ones. So that's good. Let's look at an example. This example says that there's hot air that's flowing into a pipe system. And this hot air has a certain mass flow rate, 0.05. And this pipe has a diameter of 0.15 meters. And this pipe is in a crawl space of a house. If you live in a HDB, you don't have crawl space. Crawl space is if you have a private property, under that house there's a little bit of air gap, and usually the air gap is used to either cool down the house or to provide your insulation, because air is a good thermal insulator against a cold ground. So that's why houses are elevated with a little bit of air gap. So that is what we call the crawl space. So hot air enters at 103 degrees Celsius and it exits at 85 degrees Celsius. The length of the pipe that we are concerned with is 5 meters. And the heat transfer coefficient between the duct outside, the duct outside, the heat transfer coefficient over there is 6 watt per meter square Kelvin. And that ambient temperature is at 0 degrees Celsius. So a lot of times, some of these textbooks, they come from cold countries, yeah? So they talk about their ambient is 0 degrees Celsius. So in Singapore, never. Maybe recently about 25, 26 degrees Celsius. It has been very cool in these few days. But you'll find that a lot of examples, they give you things like that sort of ambient temperature. If you look up certain textbook, when they talk about room temperature, your room temperature is 25 degrees Celsius. That is our air-conditioned room temperature. Our room temperature out there is 35 or maybe 32. So please take note that when you look up textbooks, be aware that these are written in cold countries, so they have a different ambient temperature. So in this case, it's winter time, 0 degrees Celsius. Now, what I want to point out is this part over here, the question part. Calculate the heat loss from the duct over length L. I always emphasize to students, when you read the question, in your mind you should translate it into its respective symbol. So in this case, what do you think the symbol is for that question? Question 1 over here, heat loss. What is that symbol? It's Q. Yeah? Q, we know it as heat transfer rate. But the units of Q is actually in watts. And that watts sort of like tells you that already. And in this case, that heat transfer rate refers to heat loss. Heat loss. Why is that heat loss? That's because you have fluid that's entering at 103, exiting at 85. That means heat is actually transferring out radially along the way. Why radially outward? That's because your ambient temperature is at 0 degrees Celsius. So heat transfers from hot to cold, so it's transferring outward. So this kind of thing is not going to be mentioned in the question. You got to look at the question. Understand where is the heat transferring. If I have a hot pipe that has a fluid flowing from one end to the other end, and the ambient is cooler, automatically, you don't have to have any mechanisms coming in between. Automatically, heat will get transferred out. That's what it is. You don't need like special things to arrange. As long as there is a temperature difference, heat will automatically get transferred out. So in this case, it's asking you what is Q. And how about the next question? Determine the flux, heat flux and the duct surface temperature at at distance L. So heat flux will be Q S double prime. Right? And your dot surface temperature, that refers to Ts as a surface at your L distance away. And L over here is 5 meters. So those are the questions. The notes actually included some of this kind of like telling you what to find out. So normally what I do is that when I look at the question, I'll try to have some of these symbols outlined so that it helps me. Some assumptions over here. And it also refers to a table. So this table is for the Incorpora textbook that we are using Coleman. So Coleman is A-5. So if I look up A-5, I'm going to bring it up. A-5, is it here? Is it? So these are your properties of air. Because in the question it says that it's not water, but hot air that flows into the pipe. So I'm looking at this table. You don't have to memorize this table. You can't memorize it anyway. So if needed, this will be provided during the exam. But for now, if you do attempt any questions, you could look up that table. It's in your appendix section. So the temperature, you could see that there's a list of temperatures over here. Different density, different specific heat, different kinematic viscosity, different dynamic viscosity, different thermal conductivity, thermal diffusivity, Prandtl number. So please have a close look at what you can find from this sort of table. And you can see that for different temperature change, there's correspondingly different properties values. So we're going to find out what sort of temperature we're interested in and pick up that information. So you would see that the kind of temperature that we're interested in is actually your T mean, which is your bulk fluid temperature. So sometimes this is also known as your bulk mean fluid temperature. And what that means is that it's equal to your T in plus Tm out divided by 2. So in this case, that's 103 plus 85 divided by 2. That will give you 94 degrees Celsius. Convert that into Kelvin, that means plus 273. Some students write plus 273.15. You could both take it correct. So tell students, don't waste time. You don't have enough time in that. It's 273 that we do. So 367, because plus 273. Why do I convert it to Kelvin? That's because in your table, this is listed as in terms of Kelvin. Later on, I need to see, do I need to interpolate? So at 367 Kelvin, I need properties like thermal conductivity, specific heat capacity, my kinematic viscosity, my Prandtl number. So 367. 367 resides somewhere in between here. That means we need to interpolate. Okay? And need to interpolate big time because there are so many parameters. Let's take just one example how to go about doing interpolation. Take the example of thermal conductivity. We want 367. So it resides in between these two guys. Over here, for thermal conductivity, it should reside somewhere in between these two. So what I'm going to do is to write down these two numbers and these two numbers, and then I'll do one interpolation. And please use the same method of interpolation for the other properties. This is how it goes. your temperature in Kelvin. I have that at 350 and 400. And the temperature that I'm interested in is 367. For thermal conductivity of the air, I have that. I have that, if I look at that table, it's 0.03003, and thermal conductivity of the air that I'm interested after interpolation, and the respective corresponding thermal conductivity for 400 degrees Celsius. So now, last lesson I said interpolation is a mathematical thing. You should know, but I realized that maybe you don't know. So no problem. I'll walk you through. For interpolation, normally what you need to do is to look at this part here as unknown. This one is known already, 367. That's when you want to interpolate. So you write Kf multiplied by this smaller number, and then divide this by taking the larger number minus the smaller number. And this whole thing equal to the same kind of pattern that I did. Take this minus this, divide by take this minus this. So I'm going to do the same over here. Take this minus this, divide by take this minus this. So that will be 367 minus 350, divide by 400 minus 350. And there's only one unknown over here, so K there. After doing your calculations, you will get K is equal to 0.0306 watts per meter Kelvin. So you can do the same for your kinematic viscosity. You can do the same for your specific capacity, and do the same for your Prandtl number. That interpolation. Usually, each of these interpolation worth 1 mark. So please do your interpolation well, and do your interpolation in such a way that you're so good in it. You just need like a split of a second to do the interpolation. Don't waste too much time in writing it out nicely. So you need that. You need that skill. So you'll find that for your other interpolated values, it has been solved already. What's that? So what?
I think the answer is wrong.
Which answer? This one?
Yeah.
Over here. Oh, you mean you interpolated, calculated, and it wasn't? What was the number?
0.03126.
126?
Yeah.
What I've done is to use the Holman table, but this one I think it uses another textbook table, so you get to this value. Right? So in an exam, you are given only one table to interpolate from, but in this case, since it's open, you can use any textbook. So the textbook that they use interpolate to this number. So you can write this number, no problem. Just that I'll be using this to solve. Now I would want to go ahead to try to solve this question, but I think we can go for a quick break and then we'll be back by 10:08. Go for a quick break and then we'll continue to solve.